this computer. And we're starting this presentation about polars. So polars is similar to Pandas module. So it's a module for tabular data, two-dimensional arrays. Similar to Pandas, it has bindings to both Python and JavaScript, Node.js. So far, it's growing very fast. It's much faster than Pandas. It takes less memory. It has many other advantages. And we'll be talking about all this stuff today. So you see Pandas on the left and polars on the right. So polars framework was developed by Rust community. And currently there are more than 200 contributors, more than 16,000 stars. It's a big project. But it was initially released in September 2020, and you can find even earlier publications like in February, March by Richie Vink, who is the original developer. And here I provide some links to his articles and videos and his GitHub. Also important, Matt Brubeck and Ralph Jung, and well, many others. So you see here the pictures, and on the bottom I put some links. So this is the main website, and this is PyPy, where you can learn how to use it, but it's pip install polars. It's easy. There is a GitHub repository. There is a book. There is a very good documentation on this website. And this is actually GitHub repository for the book. And that's a good article on Towards Data Science showing, comparing Pandas with polars and also doing speed comparison. And again, notice contributors, 190. Okay. Issue 645, whatever. Fork star 16, yeah. So 200 contributors. Okay, good enough. It's great. Okay, there is a book which you can use, which is actually very good documentation here. So expression, context, group by, folds, and in Python and in Rust, right? And again, from this article with this link, this table shows comparison for some operations between previous Pandas, Pandas 2, which was just recently released, and polars. And let's start from the bottom. For example, loading data. And you see polars is hugely faster, right? Transformation, again, faster, like twice faster. Extract from Parquet file, twice faster. The only where it is kind of on par with the new Pandas is extracting CSV, although frankly people use CSV less and less, especially for big data. People using Parquet mostly. So it is faster. New Pandas is good. It's much better than the previous one. It uses Apache Arrow, which means standard format and much faster file readings. So faster file operations, uses less memory, copy and write optimization, whatever. So this is another comparison. And here they try to find which files to use, like which are the fastest. Well, you know that CSV are slow. Well, it looks like here, for example, okay, this is time, load time. JSON is the slowest. Okay, this is JSON. It's very slow. So loading something from JSON. CSV is also not good. And here you have Parquet, and you have, I don't see exactly what it is. Feather. Oh, Feather and Pickle. Okay, so it's between Pickle, Parquet, and Feather. Mostly people use Parquet. I sometimes use Pickle. I don't know, but you see, Feather here is much faster, right, for saving. Well, it depends. Sometimes you just use Parquet because you want to be compatible with other people. So this is example how you do it in Pandas. And yes, read pickle and read parquet. And by the way, in polars, everything is very similar. We'll see how it's done. Okay, so key points switching from pandas to polars. So polars rows are indexed by integer row numbers. There is no label or multi-index. So in this case, it's simpler. Frankly, this is how I like to work. I never use complicated indexes. I usually just use index as like row number, 0, 1, 2, 3, and so on. Polars uses Apache arrow arrays to represent data in memory, while Pandas uses NumPy arrays. Well, the new, it's not true for the new Pandas. It can use Apache arrow, I believe. Polars can convert data to NumPy format with the toNumPy method. Yes, you can say dataframe.toNumPy, or you can say series toNumPy. But it's also not a problem for Pandas. So, okay, polars is written in Rust, runs many operations in parallel, multi-threading. This is really good because what you can do, let's say you're reading big CSV file which has, I don't know, 50 columns, but you only will use 10 columns. In Pandas, you will read the whole file, all 50 columns, and then you can delete 40 of them, right? But in Rust, in polars, what you can do, you can make it as a lazy read and delay reading to the point when you actually start using those columns. And if it sees that you're only using 10, it will only read 10. So it saves memory, a lot of memory. Okay, in parallel, eager and lazy evaluation, which I just said, polars has its own syntax that runs faster than pandas-like syntax. Okay, select columns, select rows. We will go through this in the notebook. Scan CSV. Okay, read CSV reads the whole file. Scan CSV is lazy. And it can also be scan parquet or whatever. So this is example of grouping operation. So you say data frame, which is a polars data frame. And here it's not pandas, it's polars. Group by, aggregate, sum, and then collect. So what's happening here, this may be run in parallel, and then it collects all the results together in one object. Okay, this is just examples of syntax. You can add columns, you can assign value using a mask. It is similar to how it's done in Pandas, but not exactly like that. So what's here is happening, you're saying when column C is equal to 2, then you return value in column B. Otherwise, you return value in column A. And you will call it column A, right? So what we're doing here, we're putting value from column B or A into column A for certain values of column C. So it's like update with the where clause. Similar things you do with pandas all the time, but you see syntax here is different, but it's not difficult to understand. Okay. Window functions. Okay, you can do all kind of group operations. We will go through some of that. In polars, null is a Python none. Okay, this is a big difference. It's a Python none value and can be in all columns, including integer type. So this is good. The most common gotcha and complaint about pandas was that it cannot have nulls in integer columns. And if you have nulls, then the type of the column will be silently converted to float, which is not good. So in polars, null is Python none, right? Let me make, please mute yourself. Okay, red. And NP none is not null. So this is interesting, right? But you can easily convert. You can convert not a number into Python none, and then there are many functions to help you with missing values. Okay, like is none, is null, fill none, fill null, and so on. Okay, missing data. Okay, here it gives some examples, but again, we will see it in the notebook. Okay, this is a small like table comparing operations. And you see, for example, in Pandas, you can say first row, first column, and you can do the same in polars. Or you can do slicing, or like you can go by the name of the column, or like there are many, like syntaxes is a little bit different. Like here using filter. But again, we'll see these examples. But it's not difficult to learn. And having these cheat sheets, this is actually from this link, which it's a Polars Pandas cheat sheet. It has like after about half an hour, maybe an hour playing with it, you'll feel comfortable. Reduce multiple numbers using mean, like you see the same thing. So aggregation, add new column, rename column. How you do it, you provide a dictionary, old value, new value, same here, rename. How you drop columns, sort values, drop nulls, and drop duplicates, right? So you see all operations which you're accustomed to in Pandas, they exist, and there are many others. Okay, another thing I want to tell is about Codon. It's a Python compiler. It actually unbelievable thing. So it is a basis of PhD work at MIT, and it much faster than plain Python. And they say that it's like 10,000 times faster. It's probably because it's parallelized under the hood. Like I don't know how exactly it does it. And you can compile your whole code using Codon compiler, or you can compile just pieces of your code using decorator. So again, this is something to consider because suddenly with regular Python, like slow Python, you can run with the speed of C and even faster, right? Negative part here, it doesn't support NumPy, Pandas, scikit-learn, and so on. So maybe I should make it red so it will be easily notable. Right. Okay, so next we will go for the demo to show you how things work. It's in my GitHub account, repository called Python Tutorials, and over there is a p01 underscore polars.ipynb. Come on. I will, how to get rid of it? Just a second. Okay. So this is the notebook. Okay, and let's go through it. Come on, come on. Why is it down again? Okay, so first it just repeats that it's fast and memory efficient. Memory efficient, you know what it is? Like you can take data which doesn't even fit in your memory, and Polars can process it because it will process it piece by piece by piece. It's using streaming technology in parallel and in streaming. So it can process data which is bigger than data on your computer. It's amazing. So it's written in Rust using Apache Arrow, can handle more data than fits in memory, hybrid streaming, lazy, eager execution, multi-threaded, single instruction, multiple data, query optimization, and so on. And these are some links. Okay, so let's do that. So first, let's restart and clear output. And let's go. So first we import polars and numpy, and here we're getting a CSV file. So it's actually from this CSV URL, and it has some data about flowers. And I just saved it locally in data iris CSV. So I check if it exists, I read locally. If not, then I read from this URL. I add column names, and then I write into a CSV file and into Parquet file, just to show you how you do it in polars. So df, you see PL, instead of PD, pandas, you use PL, right? So here we do import polars SPL, right? Okay, so we have a data frame, which is polars data frame. We write it to CSV, we write it to Parquet. You can also read CSV and scan CSV, read Parquet and scan Parquet. Scan means lazy. So the actual reading is delayed until the data is actually used, so that it will read only the data which actually needed. So it's optimization. Okay, here I create a copy of the data frame. In Pandas, we use copy command. In polars, we use clone command. So we create a clone of the original of the data frame, just in case if I'll need it. Okay, and here I display a head of first 3 rows, tail of last 3 rows, and I also look at one row. Like when you look at one row, you provide like index of the row and index of the next one. It's kind of Python notation. So let's do it. Okay. So this is the header, this is the footer, and this is this one row, right? So it's row number 1 here, 473213, 473213. Okay, when it shows you the shape. It gives you the names of the columns. It gives you the types, like this is float 64, this is string, right? Okay, so this is, I think, clear. Now, here we select subset of columns. So we say data frame select polars columns, and you give it only the columns you want. So these are these 2 columns, cpal length and class, which is the last one. And then we print it. Okay, let's do it and see what it gives us. Okay, total rows 149, and this is what originally we had, right? So this didn't change. And here we did head. Head by default gives first 5 rows. Well, unless you change and put some other number, like we did here with 3. Okay, next, the filter. Instead of data frame query, and here we do df filter, polars column, cpal length more than 5, right? And then, so let's see what it shows. And cpal length here is more than 5, right? Okay, so next, use multiple filters at once. So here we do df filter, and we provide 2 criteria. So this is kind of like in SQL, it's a where clause. So we say cpal length more than 5 and cpal width less than 3, and then we show, and now there is only 51 rows which fit its criteria, and you can see cpal length is more than 5 and cpal width is less than 3. Yeah, it works. Okay, so next is adding new column. It's usually done with this strange syntax ls, and we give it a name. So we say with column, and you say, for example, take column cpal length, multiply by 10 the number, and save it with alias my column. And you see it did it, and you have now my column, and here it's 49, and here 4.9, 4.7, 47. So this is really, it multiplied those values by 10 and created a new column. Okay, next, group by and aggregate, right? So we group by class. This is class, iris citosa, whatever. And there are only 3 classes in this data set. And then we calculate mean value, right? And there are 2 ways here shown how to do this, and both work. And yeah, and they both provide the same result. Okay, alternative way: read, filter, group by, aggregate. Okay, this is interesting, right? Because what you're doing here, you in one set, you read the file, then filter it selecting by this criteria, right? Then you group by class, and then you calculate mean. And then you collect. And then you display the result, and here's the result, right? So for each class, it calculated the mean value for everything, for all. Again, you see it's not difficult, pretty intuitive. Next, missing data. So as I told you, the none is actual null, and not a number is valid float. So there are functions like fill NA, fill null, fill not a number, right? So for example, you can do fill NA with some negative number. Like this is the syntax how to do it. Null count counts number of nulls, which is Python none, values in each column, and returns as one row data frame. So it will be column name, and under column name will be number of nulls. None values are not considered to be missing data and not counted with the null count method. Not a number values are filled with fill not a number, and not with fill null. Polars has is none and fill none methods, which work similar to these methods. Okay, so let's just run, and it shows not a number at null, and okay, what do we do here? So we create this data frame which has none and it has not a number, and then it just displays the data frame and displays the data types, which is float, but I also use these defend data types just to show you how to do that. Then I do null count, and it shows null is only in this column, C1, and it shows 1, you see? And there's no nulls in the other column. It has not a number, but not a number is not considered as null. And finally, what do I do here? Oh, I fill not a numbers with none, right? And then I do null count again, and now it is 1, 1. So now it both this and this become nulls, and it counts both of them. Okay. So mean of data with non-null values excludes non-null from calculations. Mean of data with NP not a number result in not a number. So if not a number, if you add it with any other thing or whatever, it just creates not a number. Solution, you substitute nonce with none, and then they will be avoided when calculating. Like the calculation go around them, just not include them in summing up. Okay, so here is example how you do things. Let me just run it, and so it does something here. So fill null, we put what is this, lit? Okay, minus 999, okay. Fill null minus 999, okay, this is a shorter way of doing it. So again, data frame with columns, this column, fill null with this number, and it works. Okay, anyway, next is manipulating data, where I am. In data frame. So now I follow this article, which has a lot of examples. So we create this array of tuples, and we create Polar's data frame from this matrix. And in Pandas, when you create data frame, you say columns equal and give it a list of column names. There is no columns argument in Polar's data frame. Instead, you're using the word schema, and you can give it the list of column names, and you can give it like this. It will figure it out. So we're creating the data frame. It's a Polar's data frame. As usual, it shows you the shape. It shows you column name, column types. In this case, they're all integers. 1, 2, 3, 4, 5, 6, 7, 8, what, so on. Okay, good. So next we use apply and map. Again, in Pandas, you have these two functions. Apply is usually slow, map is much faster. And here is the possible syntax. You say polars column, like this column, apply, and then whatever lambda function is. So lambda function is just a very simple function which doesn't even deserve to have a name. Well, instead of lambda function, you can use a real function. You can create function before, and you can just stick it in here. But whatever. So here we use simple function which multiplies number by 2. And another way to do it, you just take the column and you multiply the whole column by 2. This is how would you do it in NumPy and or Pandas. So both syntaxes work. So df select column A and apply, multiply by 2. If x more than 5, else just leave it alone, right? So print it, and then cannot use if on a series. Okay, so what are we doing? Column A, I'm confused here, but okay, let's do it. So one, I'm really confused what's going on. Okay, first we're printing df2, right? And we're multiplying by 2 for big numbers. So 1 is not multiplied, right? If and then next is 4 is not multiplied. So the original was 1, 4, and then 7 is more than 5. So it will be multiplied. It will be 14. Yes, 14 and then 20. Okay, so it did what we wanted it to do. It multiplied numbers by 2. Next, we multiply it again by 2. Now we removed this if, and I don't remember, we cannot use if on a series. What's the difference? Oh, here we use apply. And with apply, it works, right? But with map, it doesn't work because map, for map, X is a series, it's a column. So here, X is one element. So X may be like number 7. But for map, X is a vertical column. It's like an array. And you cannot use if array more than 5. So that's why for map it doesn't work. You need to do it differently. Okay, so this is good enough. Changing only column A, returning all columns. So we take data frame. We say we'll be doing lazy operation. We will select, and for column A, we apply this operation. We multiply by 2, comma, and then we return everything else except for A, right? So you see what's going on here. For one column, we make some transformation, and we return all other columns unchanged. And then we collect. And then we just print it here, and duduch. So you see that for column A, it was 1, 4. Now it is 2, 8, and whatever. It's all multiplied. And other 2, 3, 5, 6, whatever, they're not changed. Okay, good. Multiply column A by 2. Store the result in a new column A2. So how we create a new column? With the word alias. So we return all columns, including A, then comma, and then we take column A, do some calculations, and save it under name A2. And it should work. And yes, and we have A2, which is twice bigger numbers than in A. So it worked. Applying function to rows. Okay, so we create this simple function which takes something, prints it, and returns it, right? So does nothing. But then we take a data frame and we apply this function for the whole data frame, right? So let's see what it's doing. So first of all, we do this. We put the result in df2, and then we draw the line, and then we display df2. So what is df2? Well, here it is printing as it is running these tests. So it looks like it's printing tuple for each row. So remember how it was 1, 2, 3, 4, 5, 6. So that's what it creates. It goes row by row, and then it returns row, right? And then df2 is df apply, and what we see here is actually a data frame, right? I cannot actually explain in detail myself like what exactly is going on here. So it looks like it's a way to go row by row, right? Okay, anyway, I want to continue. Let's go further. Okay, next we will be doing what? Perform an integer division of all the numbers in a row by 2 if the sum of the numbers in this row more than 10. Okay, so df apply, and then we do lambda x, and we create this tuple divided by 2 if sum of x more than 10, else x. So when we're doing apply and give it lambda x, so x is a row, right? So here when we do apply and giving this function, so what this does, it takes a row and gives it to the function. And that's why it was printing the row. Okay, cool. So let's just run it. And it doesn't change this. This is divided because it's supposed to be 4, 5, 6. The sum is more than 10, so it divided it by 2, and get integer of the division. Okay, so it worked, as you can see. Okay, duplicate all columns, converts a tuple of 3 numbers to 6 numbers. Okay, let me run it. So you see column 0, 1, 2, and again, 3, 4, 5, but you see 1, 2, 3, 4, 5, 6, and here 1, 2, 3, 4, 5, 6. So it's kind of duplicated it horizontally. So it took x, which we know is a row, and multiplied it by 2. Okay, let me show. So for example, if I have AA equal 1, 2, 3, and then I say AA by 2, you see, this is just pure Python. You take the tuple, and it multiplying by 2 means repeated twice. So that's all it did. Okay, next, calculate totals by column. So we just do df and calculate sum of all columns. So let's do that. And you see, for each column, it calculated the total. Very, very easy. Here, we want to take the sum row, which is this row, and we want to add it at the bottom of our data frame. So we do concat. And we say take data frame and take another data frame, which consists of just one row, and concatenate them together. And here is the data frame, and then the total is added as another row. Okay, it works. Now here we're doing summing by row horizontally. Okay, and we get the totals. So 1 plus 2 plus 3 is 6. 4 plus 5 plus 6 is 15, and so on. Okay, add the sum by row as a new column. Okay, so data frame select, select like all the columns as they are. Like you see, star means all. And then select, like for each column, we do sum on x, x is equal 1, which means horizontally, and then call it sum. Okay, and miraculously it works, and we have this sum as a new column. Okay, change a value in data frame if condition is met in another column. This is very common. This is what in SQL, when you do an update statement, for example, you say set value to something in this column where, and some values in other columns fit some requirements, like it's equal to something or less than something and so on. So here we can do the same thing. So we say data frame dot with columns, and then, I mean, this is tricky. Maybe I should probably first explain this syntax in the next cell. So we say data frame with columns, and then in parentheses, in this structure. So we do when, then, otherwise. Okay, so when B is more than 5 and C is less than 9, right? Then put the 555. Otherwise, put the value of sitting in column A, right? And put it back in column A. So what it will do, it will update column A, putting their values 555 where these two requirements are met. And we put this result into df2 and then we display it. So when we do that, here you see 555, 555. So what's happening? B should be 5 or more, that is satisfied, and C should be less or like equal to 9, which is satisfied only in these two rows. So you see it did what we wanted. Now, this example is simpler, but it's a little bit tricky. You know, in Python, you can use syntax like star in function. You can pass star and then some arguments, or star star when you provide a dictionary of arguments, and they are expanded in a function call. So here we are taking advantage of that. This A is name of the column, but at the same time it's name of the variable. See, so it's kind of tricky. So we say A, instead of doing the ls syntax, we simply do A equal. And when we do a Polaris when PL column equal 5, well, here I didn't put 2, I just put 1, like then 555, otherwise whatever, take the value of A and put it back into A, right? So it's the same thing. But here we're just using when B equal 5, so it will be only one row here. Okay, cheat sheet for Pandas and Polaris. This is something I showed in slides in the beginning. And let me go quickly. So we're creating a data frame, and you see you can create data frame same way you do it in Pandas. You provide dictionary, right? And this is dictionary. So it has keys, which will be column names, and you have values, which are lists of values. And let's do this. And we created this Polaris data frame with columns names, group, X, Y, Z, and index, whatever. We can set values explicitly. So you can take this cell in the data frame and you can put the a value, let's say 55, and then you print it. So it was 5 here, and now it is 55. So you know what? Let me do print the whole df, so you will see it here, 55. Why it is 1? Because numbering starts of 0. So this is index 0, 0, 0th row and 0th column. Okay, you can do slicing. So here we go from row 1, which is this one, to row 5,
hold on, to row 3, but not counting 3. So it'll be 1 and 2. So it'll be this row and this row. So it'll be 2 rows. Yes, exactly right. Okay, next we're taking all rows and we're taking columns except for the first one, for the 0th one. We start at 1. So we should have all columns, but we will not have a group column, right? So let's see how it works. Yes, we have XYZ and index, but we don't have group. Okay, row indexing by label, okay. So we say that index column equals C. So this is C, right? And we say filter, give me only the rows which satisfy this. And in this case, it's only one row, and it returns you a data frame. Okay, good. This is example of column indexes by label. So we select, okay. So what do? This is one way to do it. So both of those things, both of these lines do the same thing. We select column X and all rows. So you can do it like this, which is similar to Pandas, I guess, and we can do it with a select word, same result. Okay, column indexes by labels. You know what? I just want to go through it faster because it's all quite obvious. So here, for example, we go all rows and we go from X through to Z. So it goes X, Y, Z, right? So it, okay, mixed indexing. So you can index both column and row. You can use mean, sum, and so on, doing some aggregation. This is example how you do it for Z column. You can add new column using alias. We already have done it before. Here, Z1, we create this column Z1. You can rename column using a dictionary, right? Here, X is now called X new. We can drop column. We just provide names of the columns which need to be dropped, and it will drop it. Here you see they disappeared. You can sort. By the way, it didn't drop like in place. This is what it returned, but the original DF still has the columns X and Y, so you can see it. So here we're sorting by X column. Here we drop nulls. Did we have nulls? Yeah, we have null here. So it will drop this row, which had null. So number 2, 1, 9 null, F. Yeah, here we don't have it. We drop nulls. Select unique rows. Okay, concat, extend, and vstack. So these are 3 ways how you can combine data frames together. So concat, 2 data frames, df1, df2, copies all data to a single new location. vstack doesn't copy data, it just links the new data frame to the existing 2 locations in memory. And extend copies the data from df2 and appends it to df1, right? So if you do concat, it will just create a new data frame, and you see what it did. It took like these A, B, C, D, E, F, and then again A, B, C, D, E, F, and this DF is the same 2 DFs. But you cannot do the same using extend command, like instead of, because then it will try to extend itself. So you need to have these 2 data frames different if you're using extend. So here I'm doing this. First, I'm creating another data frame in memory, call it df2. It is clone of df. And then I do df2 extend using df. And then I get the same result. Okay. Counting number of nulls in the whole data frame. Well, you already know that there is a function called null count, which for each column gives you number of nulls. But if you want to count total number of nulls in the whole data frame in all columns together, I didn't find a function for that, so you have to manually add these numbers together. So after I created this small data frame, which for each column has the number of nulls, I go through these columns for column in the different columns, and I add this number, right? It has only one row, like it's a 0th index. So I add this number and then I print it, total number of nulls. So it's a simple thing. So this is the result of null count. So it shows you number of nulls in each column. And this is total number of nulls, which is 1 plus 2 plus 1, it is 4. Okay. Now, transpose function. In Pandas, we have a simple way to transpose. You just do data frame dot capital T to transpose, but there is no function like that in polars. So here I just wrote a small function myself called T, which just goes through rows and columns and populates the new data set. So here I take this data set, create a data frame, then I transpose it, and then I print it. And here you are. So here we were by column 1 to 3, and here this 1 to 3 goes by row. So it was in fact transposed. Okay. Get column values. In Pandas data frame, you usually do dot values, but here you can use toList. And it gives you 1 to 3. Instead of toList, you can do toNumPy. So this is example toNumPy, and it gives you 1 to 3 as a series here. And then you can do series toNumPy. And this is example of convert polar series to NumPy. Oh, here I print this NumPy array, and it gives me 1 to 3. And then I say, okay, this array plus this array plus this array. This is how NumPy works. When you array is like a vector. If you're adding vectors, each element of the vector I added together. So here we get 1 plus 1 plus 1 is 3. 2 plus 2 plus 2 is 6, and similar to the last element. So it's really NumPy. Yeah, and convert the whole data frame to NumPy. Oh, there are multiple ways of doing this. Some people, well, in Pandas, I believe there is a frame command or matrix or something which just gives you this. Here you have to do some sequence of commands. You can also save it to file and then read from file. Here's an example of converting between Pandas and polars. So you see here I imported both of them just to make it visible. So I create a Pandas data frame, PD data frame, I print it. Then I say polars from Pandas data frame, and it creates a polars data frame, I print it. And then I do df to Pandas, and it returns another Pandas data frame, and I print it too. So here is an example. So this is Pandas data frame, this is a polars data frame, and this is Pandas data frame again. Well, we went very fast through many examples, but I think you see it's not difficult to work with polars. It's very similar to Pandas, and there is a lot of documentation. There is a lot of Stack Overflow. It existed for about 2.5 years, and I think we're really ready for prime time. Rust is a very well, how to say, it's very stable, right? And it helps to create software which is reliable. So we're there, we can use it. Okay, I'm stopping the recording.